Welcome to the UGC lecture series. In this lecture we are going to talk about B trees. Now, before I go and discuss B trees with you, I want to tell you about certain facts that we have looked at sorting from two viewpoints. Remember the internal sorting and the external sorting. You remember what was internal sorting? Internal sorting was sorting which was done exclusively in the main memory, while external sorting, in addition to doing sorting, was more concerned also with how the records are brought in from secondary storage. And most of the issue was that we wanted to sort records, large number of records that were available in the external storage. Now we are going to look at B trees. Why am I talking about that issue? Because B trees is also concerned with the organization of data from the external storage viewpoint. So we are going to talk in terms of blocks, we are going to talk in terms of how blocks are brought in from secondary memory to primary memory or main memory, and we are also going to talk about the organization in such a way that we want the idea of the B tree data structure itself is to reduce the number of disk accesses. That means the organization of the block should be such that you bring in the correct number of blocks at the correct time and you do the operations. So this is a data structure or a tree. We have seen a number of trees like binary tree, general tree, binary search tree, we have looked at AVL trees. All those were trees which we assumed were completely stored in the main memory. Here we are not assuming that the data associated with the tree is stored in the main memory. We are assuming that some of that data is stored in the secondary memory, and in fact the whole data structure is oriented towards data that is stored in external memory. So with that slight introduction, let us go on to what we mean by B trees. So as before, we are going to talk about the objectives, why B tree was designed. So the design of the B tree itself was oriented towards external storage for database management system. Where we looked at previously of how file was organized, external sorting was done with respect to database management system. You must remember that database management system is one of the main applications of computer science, and so lot of attention has been given to how data is organized and how data is sorted in those type of applications. And when you talk about database management system, you are talking about a large number of records. You can think of bank records, students records and so on, which is stored in, cannot be stored in the main memory. So some of it is stored in the secondary memory. So in this lecture we are going to talk about index sequential files, and then the motivation for B trees and the definition of, and what is a B tree. Okay. So that is what we are going to talk about in this lecture. So now we will talk first about index sequential access. Though we have looked at it slightly in other lectures, we are going to go a little more in detail, and in this lecture we are going to talk about, we are going to take the index sequential files in such a way that it leads you to a need which the B tree is going to fulfill. So up to this point we have had to choose between viewing a file from an index point of view or from a sequential point of view. Remember what is an index viewpoint? An index was a pointer or a address in a sense, which gives you the location of the records. It will not be one record. If it is a one-to-one index, then it is equivalent to having the record itself. It is just a sequence of records will be indexed by one index value. For example, if I say that it is ordered according to the keys, and you have keys ranging from 100 to 1000, you will say you will have an index to the 100th, the record containing the 100 key, and then maybe for 200 you will have one. So 100 to 200 values will be stored sequentially there. That is why it is called index sequential file. You go through an index into one location and from there you search sequentially, then next index will give you a sequential. So it is stored in sort of blocks like that. Now we are looking for a single organization that will suit both indexed and sequential organizations simultaneously, both the views, that is index view as well as sequential view. So please remember what is an index view. Okay, an index view is your Okay, for example, to understand better about what is an index, you can think of a book in which at the back you have the authors and all that. With that author you can go into the location in which the page number will be given, and you can go into that page where you will find that author's name. This is a typical example of an index. It is in fact called book index. In fact, in a library also you can have these, it will give you where exactly that number is stored, and you can go and look, they are located there. So, it basically gives you a location in terms of some key value. Okay. So, why do we want to see both the index and the sequential simultaneously? So, if you look here, if an application requires both interactive random accesses as well as consequential batch processing, both sets of actions have to be carried out very efficiently. That is, you have to locate it as well as you have to do some operation sequentially. In that case, if you want interactive, it is random access. If you want to do sequential batch processing, it is sequential. So, both the actions, it is not that one should be inefficient and the other should be efficient, both should be done efficiently. So, for example, a student record system in a university is a typical example where you need both types of views. So, in order to do that, we have not come into B tree, yes, remember we are going towards a motivation for B trees as I told you in this lecture. So, we define something called a sequence set. Now, a sequence set is a set of records in physical key order which is such that it stays ordered as records are added and deleted. So, for example, I can say that a sequence set will be a set of records that are stored in memory in sequential order. For example, 100 to 200, that would be a sequence set. Now, when you bring in a record, say for example, you have 100, 110, 120, 130 and 140 and 200 like that. Now, suppose you bring in 115, in that particular localized place you will put it in the correct place. So, it always remains sorted. So, that is the meaning of a sequence set is a set of records in which physical key order which is such that it stays ordered even if you delete records or if you add records. Okay. Now, since sorting and resorting the entire sequence of set as records are added and deleted is expensive, we look at other strategies. Now, this is very important. One easy way of doing all this is to have the, suppose you have 10,000 records, keep all the 10,000 records in the sequential order, and then if you insert and delete one, you reorder and resort the complete sequence of records. But this is a very expensive operation. Why is it an expensive operation? Again we come back to that block, because you have to access time, you have to, it will be stored in different tracks, different sectors, and so the disk access time is going to be very high. So, it cannot be done that way. So, what we are trying to do is we are trying to localize the changes, that is we are going to say that I go inside here and here alone I will maintain the sorting. So, that is the localization. So, the idea is to use blocks that can be read into memory and rearranged quickly. Now, when I want to sort, I will see that it is localized, it is a minimum block size, and I bring it into the main memory, and after I put it in the main memory I do the sorting. This is a very quick operation. So, like in B trees, blocks can be split, merged or redistributed, the records can be redistributed as required. Now, using blocks we can thus keep a sequence set in order by key without ever having to sort the entire set of records. That is the main issue. So, now we are talking about three things, one is the index, one is the sequence set, and one is the block size and the main memory. So, what you have is you have a sequence set, the sequence set will be approximately equal to the block size approximately, and then what you do, this sequence set you will be able to maintain because you are having a block, and the block can be brought into main memory and you do all the operations in the main memory, but you are never going to at any point of time sort the entire set of records, because that will be a costly operations. You cannot afford to bring the complete group or set of records into the main memory, it is not feasible. So, and if you want to bring it and sort it like that, you will have to keep on doing block, take it from the second memory, put it back in the main memory and so on, which is a very costly operation. So, this is the use of blocks. Now, even if you are going to use blocks, there are certain costs associated with this approach. A block file will take up more space than an unblocked file because of internal fragmentation. I will just explain what is meant by internal fragmentation. Suppose I have a block, okay, of say containing 100 records, okay, I am fixing my block size to be 100. Now, what happens is sometimes even if I have only 70 records, I have to put it in this 100 block because that is the size of the block. So, internally that like that I can have different blocks during different sequences of insertion deletions. One may have 70, one may have 80, one may have 90, and total altogether you have 30 plus 20 plus 10 which is 60, but I am not able to use that 60 because these memory gaps are available across different blocks. So, this is called as internal fragmentation because you are allocating more than necessary to that particular set of records. So, that is why you always say that block records will occupy more space than unblocked records. In unblocked records you are only giving it as much storage as it actually necessary, while in a block you are giving it more than necessary because what can fit in a block only you can give. So, if I have say blocks of size 50 and 100 and I have one which 60, I cannot give it to 50, I have to give it to 100, but 40 will be internal fragmentation. This is just an example, do not take these numbers very literally. Now, the order of the records is not necessarily physically sequential throughout the file. Okay. The maximum now this is what we are trying to say, that inside the sequentiality as it is so called is not maintained throughout the entire. Suppose you have 10,000 records, it is not to say that all the 10,000 records are ordered sequentially, it is not ordered sequentially, but what we are ensuring is that within a block it is ordered sequentially. So, you have different blocks and within a block it is ordered sequentially, and you know which block comes after which block because that is the way you have ordered the blocks. This way you are ensuring that within a block it is ordered sequentially, though physically it need not be ordered sequentially, logically it is ordered because of this block linking. Now, an important aspect of using a block is to the choice of the block size. You have to decide what should be the choice of the block size. If the block size is too large, you will have internal fragmentation. If the block size is too small, you will have too many reads and writes or too many disks reads. Okay. So, there are two considerations as I already told you. The block size should be such that we can hold several blocks in memory at once, that is you should not have only one block in memory, then you are giving only one part of the file more concentration. The block size should be such that we can access a block without having to bear the cost of a disk seek within the block read or block write operation. The idea here is that when I must ensure that the block size is not too large. So, I have remember the disk access, I am assuming that the block is stored in the same sector in the same track, that must be the size of the block. So, these are the two things we have to consider, that is when we are accessing a block without having to bear the cost of a disk block. So, what we do, the next step is each of the blocks we have created for our sequence set contains a range of records that might contain the record we are sorting. So, now we are going to talk about the range. The range is the key values that are stored in that particular block. The range is the range of the key values that are stored in that particular block. Now, and we can consider a simple single level index for these blocks. So, the single level index will tell you that these blocks, the records in these blocks are higher than this, and the next key will tell you it will be lower than this and so on. So, with that you can have the block size. So, the combination of this kind of index with the sequence set of blocks provides complete index sequential file. This method works well as long as the entire index can be stored in memory. Remember, we are talking about hundreds and thousands of records. So, even if you have blocks, depending on the block size, the number of indexes to these blocks are going to be very large, and we assume that the index can be stored in the main memory. If the entire index cannot be stored in the main memory, then we use B plus tree and B tree plus a sequence set which holds the records, and this is what we are going to talk about when we talk about B tree. Now, let us take a small break. Welcome back after the break. Before the break we were talking about the sequence set, and we were talking about what happens when the index to the blocks that we are storing is not, you are not able to accommodate the complete index in the main memory. Now, if the entire index cannot be held in the main memory, we can use a B plus tree which we will discuss later. Before we go to a B plus tree, we have to discuss what is a B tree, because the B plus tree is based on B tree, and also an index which holds the sequence set which holds the records. Sequence set, remember, is physically they are all, Sequence set is the set of records that falls within the range. So, if you have that sequence set and you have an index that is stored as B plus tree, it is not necessary that the index has to be completely in the main memory. So, that is the issue we are going to talk about. What is the content of the index that we are going to talk about? Now, the index, remember, if it was you are able to store the index completely in main memory, then we do not have anything to worry about. But what we are trying to tell here is the index cannot be stored completely in the main memory. So, let us look at what the content of that index is. The index serves as a kind of roadmap for the sequence set. We do not need to have keys in the index set. It just gives you a sort of roadmap. This is where you will find the index. That is what it is trying to tell you. And I mean this is where you will find that particular sequence set. That is what it is trying to tell you. What we really need are separators which are capable of distinguishing between two blocks, this block and that block. What is the separator between the two blocks? This is what we need. Okay, so we are going to use separator instead of keys. Now, we can save space by using variable length separators and placing the shortest separator in the index structure. Now, the keys can be very large and we can save space by using a variable length separator and placing the shortest separator in the index structure instead of having the complete key in the index structure. What we need essentially is that I must know the separators between blocks, and so I am going to use a minimum separation minimum data that I need to know the difference between the two blocks or separation between the two blocks. So, the rules are, if key is less than the separator, you go to the left, if the key is equal to the separator, you go right, and if key is greater than the separator, also go right. I will explain this a little bit further as we go along. We will talk about B plus tree, but we are going to first we will bring it into go into the topic with B plus tree, but we are going to talk first about the fundamental, that is B tree, and then go on to B plus tree. Now, the separators we just identified can be formed into a B tree index of the sequence set of blocks, and the B tree index is called the index set. And along with the sequence set and the index set, it forms a file structure, then you call it a simple prefix B plus tree. So, I will repeat again. The separators that you have identified are now going to form a B plus tree index, and the B plus tree, that is which is called the index set, and that index set along with the sequence set. Remember what is a sequence set? A sequence set is the number of records that are stored in a block. Okay. So, that forms a file structure. So, simple prefix indicates that the index set contains shortest separators. We are not going to keep the whole separators. What you need to separate out only we are going to keep, or prefixes of the keys rather than the copies of the actual keys. This is the main idea. We are not going to keep the actual keys, we are going to keep the prefixes of the shortest keys. Our only consideration is that I must be able to separate out between the main tree and between one block and the other block, or one sequence set and other sequence set. So, now what the idea is that the changes are localized to single blocks in the sequence set, and make the changes in the sequence set and to the index set. You do not have to go and search the complete set of records to make any changes. Whatever changes are there, you only do it to a single block. Changes involving multiple blocks in the sequence set are also possible, but that is very rare. And I am still talking about B plus tree. If blocks are split in the sequence set, a new separator must be inserted into the index set. So, if the number of records added is such that it cannot be accommodated into a single block, then in that case you have to separate out the block or split the block, and then you have another separator that you have to insert into the separator set or index set. And similarly, sometimes the block size may be too small to be maintained. So, if you then in that case the blocks are merged in the sequence set, and then a separator must be removed from the index set. If the records are redistributed between blocks in the sequence set, the value of separator in the index set must be changed. So, I will repeat again. See, remember you have a block. Okay. Now, one thing that can happen is that the number of records that you have to store becomes greater than the size of the block or sequence set. Instead of calling it block, I will call it sequence set. It will be greater than the sequence set, which means that now I have to split this sequence set. If I have to split the sequence set, then one key has to be added into the index or separator. Instead of saying key, we are using the word separator, because separator is a prefix of the key. So, the separator has to be added into the index set. That is the first condition. Now, the next is, sometimes what happens, the blocks or the sequence set are so small that you have to merge them. If you have to merge them, then what happens, a separator that has been already there in the index set has to be removed. Now, sometimes what happens, the records have to be reordered between, if it is within a block there is nothing you have to do, but if it is between multiple blocks in the sequence set, in that case what you have to do, the separator in the index set also has to be changed. So, this is the fundamental of the B plus tree maintenance. So, with that basic idea we will go into the data structure. Now, up to now we have not spoken anything about the data structure, what is the condition of the tree, we have not spoken anything of that, only that is what we are going to talk about now. Now, the motivation is when the data is too large to fit in main memory, then the number of disk accesses become important. I have already told you this, because the block should be such that whatever operation you are doing, you localize it within a block, so that you do not have to go and get different blocks from different places and have number of disk accesses. Disk access, as I already told you, is very expensive compared to typical computer instruction, because of mechanical limitations, because you have to go, the head has to go reach the track, then reach the sector because of rotational delay. So, seek time and rotational delay together causes disk access time to be very large, and it is considered the very expensive operations. That is why all this data structures has been organized. So, it is said that one disk access is worth about 200,000 instructions. Of course, as the speed of the computer becomes even more faster, this can increase, but at the same time the disk access time is also increasing with more sophisticated disk heads and disk writes and all that, and the number of amount of data you can store on a disk, but still it is approximately this value. So, you can see that the disk access you must avoid at all costs. So, even in the main memory, when you do efficiency of program, you are talking about instructions. Here we are talking about 200 instructions for one disk access. So, the number of disk access will always dominate the running time. So, it is our duty here to reduce this disk access as much as possible, and that is the complete motivation for this organization. So, the secondary memory or the disk is divided into equal size blocks. Typical sizes of blocks, as we already told you, there are different considerations, but normally it is divided into 512, 2048, 4096 or 892 bytes. The basic IO operation transfers the content of one disk block to and from main memory. So, when I say read something, it is actually reading a block into a buffer. I think this is you would have studied this in computer architecture. You are actually doing what, when you say basic IO operation, you are reading one block into the buffer. Okay. And our goal is devise a multi-way search that will minimize the file accesses. So, meaning you are going to exploit the fact that when you say read, you are not reading one record, but you are reading a block of records. So, you do the search in such a way that whatever I will need will be in this block. Okay. So, that is what we are trying to do. So, before we go further, let us look at memory trees. So, here if you look at keys are K1, K2, they are actually separators, but anyway K1, K2, K3, K4. I will have a tree here and I will have a tree here and I will have a tree here. Now, here the key, the key of whatever is stored in this is less than K1, that is my property. What is stored in T2 will be between K1 and K2. What will be stored in T3 will be between K2, K3. What will be stored in T4 will be between K3, K4, and what will be stored in K5, T5 will be greater than K4. This is what is our premise. I will repeat again. So, if you have any memory tree, this is not typically like a binary search tree, it is little different, that is why you have to understand that concept well. So, here I have subtrees T1, I will have one T1, T2, T3, T4, T5, I will have 5. So, when I have 5, this all the keys here will be less than K1, will be less than K1, here will be less than between K1 and K2, here between K2 and K3, here between K3 and K4, and here above K4. So, a node first of all contains multiple keys, and the order of subtrees is based on the parent node keys. If each node has m children and there are n keys, then the average time taken to search the tree is log m to the power of n. This is very important. So, how do you search memory tree? For I is equal to 1, I is less than or equal to m, you visit the subtree to the left of ki, visit ki and visit the subtree to the right of km minus 1. So, that is the search tree. So, it allows insertion and deletion into the tree structure. Remember, the tree structure is not storing the entire record, it is not even storing the key, though we tell key here, it is storing the separator actually. and it is based on the log m n property where m is the order of the tree. So, remember as you increase m, this time this value will change. The idea is that you leave some key spaces open. Now, suppose when I do this, I am storing the complete, I am filling up the block, then when I do insertion, I will have a problem. Okay. So, the idea is to leave some key spaces open, so that an insertion of a new key is done using available space in most cases, but of course, sometimes available space will not be there, then you will have to split and form a new thing, which we will see. So, it is less dynamic than our typical binary tree, okay, and it is, but the issue is it is ideal for disk based operations when we are talking about blocks of records coming into the picture. So, now let us take an example of a 2-3 tree. Now, here you have G, this is the key. Now, all nodes here will be less than G, okay, and all nodes here will be greater than G. Okay. Now, you take C, here it will be less than C, here it will be greater than C. Here you again you take, this will be less than I, okay. Here if you see, okay, now here is slightly different. If you take I, this is a 2-3 tree. So, if you take IM, this will be less than I, this will remain, this will have keys between I and M. So, JK, and here you will have trees greater than M. Okay. Similarly, if you look here, D and E, here you will have less than D, here you will have between D and E, here you will have greater than E, if it exists of course. So, that is the, I will repeat again, it is not the same as a binary tree, because we are talking about a m-nary tree, here 2-3 trees. So, the node can have maximum of 3 children and a minimum of 2 children, and if it has only 2 children, then this is similar to a binary tree, this is less than G, this is greater than G. Okay. But if it has 3 children, then left will be less than the first key, the middle will be between I and M keys, and the right will be greater than the M tree. So, let us go back and define what are B trees. It is a specialized multi-way tree designed especially for use on disk. In a B tree, each node may contain a large number of keys depending upon what is the degree of the tree you are defining. The number of subtrees for each node then may also be large. So, a B tree is designed to branch out in this large number of directions and to contain a lot of keys in each node, so that the height of the tree is small. So, if you have large number of keys and you do not allow too many children, then what will happen? The height of the tree will increase. So, our main idea is the height should be relatively small. So, what you do, you allow as many children as possible, that depends, it is an optimum value that you will have to have. So, a B tree of order M is a tree with the following properties. The root has to have at least 2 children, it cannot have less than 2 children unless it is a leaf, and no node in the tree can have more than M children. M is the degree of the tree, order of the tree, not degree, order of the tree. So, every node except for the root and the leaves must have at least M by 2 children, this is also another property we are saying, and all leaves must appear at the same level, and an internal node with k children contains exactly k minus 1 keys. So, let us look here. So, a B tree of order M, the maximum number of children for each node, is a tree which satisfies the following properties. Every node must have at most, maximum that it can have is M children. Every node must, except the root and the leaves which follow a different property, must have at least ceiling of M by 2 children. The root has to have at least 2 children if it is not a leaf node, and all leaves appear in the same level and carry the same information. So, a non-leaf node with k children contain k minus 1. Each leaf node other than the root node, if it is a leaf, must contain this. We have seen these things. So, let us take an example of order 5. Now, you start here, you have M. So, remember nodes to this is left, all these nodes subtree must be less than M, all this here must be greater than M. Now, this is a root node with 2 children, at least it should have 2 children. Now, look here, non-leaf node, it should have at least 3 children, 5 by 2, ceiling of 5 by 2. So, it should have at least 3, maximum of 5, here we have 3 and 4 as examples. So, now let us take this E and H. If you look here, the subtree here, okay, will have children less than E, the subtree here will have children between E and H, the subtree here will have children greater than H, but anyway we have a condition that it is less than M. Now, if you look at this side, this subtree will have children less than P, here you will have children between P and T, P, Q, S is less than T. Here you will have between T and X, V, W, and here you will have greater. Here it has 4 children, here it has 3 children. The conditions we have is leaf must have at least 2 children, all leaves should be at the same level, it should have maximum of m children and at least m by 2 children. The standard used index in relational database is this B tree index and allows for rapid tree traversal, searching through an upside down tree structure. Reading a single record from a very large table using a B tree index can often result in few block reads, even when the index and tables are millions of blocks in size. Even then you will need only a few block reads, that is the whole idea. So, any index structure other than the B tree index is subject to overflow. Overflow is where any changes that happen, you will not be able to add records in the original index structure, you will have to do something else. Here we are, what we are doing is we are keeping spaces in anticipating that you will want to do insertion. So, it is a multi-way tree design especially for use in the disk, as I already told you, and the B tree consists of a root node, branch nodes and leaf nodes. It is designed, as I already told you, large number of things. The insertion and deletions are simple processes, but however already full means you will have to do something which we will see in the subsequent lectures. So, this is what we have and this we have already discussed. So, in this lecture we have discussed what is the need for B trees and we have also discussed what is the characteristics of B tree, which we will explore again in the next lecture when we talk about insertion into B tree. So, what I want you to do is, what is the need for blocks in data storage, then I want you to give some typical characteristics of B trees and the connection between index sequential files and B trees has to be explained. So, this is what we discussed in this lecture. Thank you.